This video, we're going to go over the comparison test, and then the next video, it'll deal with the limit comparison test, but they're pretty much ideally the same. The name is everything. What it means, you're going to be comparing a known sequence to a sequence that you don't know. But you're going to kind of be a little smart about what you're going to compare it with. So in the preceding video, when we're talking about P series, we saw that with P series, as long as P was greater than 1, we knew that our sequence and our series converged. All right. So we're going to use stuff like that to our advantage. All right. So here's the comparison test. So suppose there exists an integer n such that the sequence is in between 0 and is in between 0 and b sub n for all n greater than or equal to capital N. If b sub n converges, then a sub n converges as well. So let me show you an example of this, and then we'll come back and we'll do number 2, which deals with diverging. Okay? So consider the sequence, or I'm sorry, the series. I keep saying sequence. The series 1 over n squared plus 1. Now, we're going to determine, does this converge or diverge? And we don't have to get real fancy with this, all right? Because this should look similar, all right? This sequence, or this series, kind of looks like this series right here. All right? And this is a known convergent P series. Like, we know this converges because 2 is greater than 1. So therefore, the only thing that we need to demonstrate, or at least understand, is that if this converges and if the partial sums of this sequence are smaller than the partial sums of the 1 over n squared series, then we know it converges. All right? So let's write out what we're saying here. So since the terms in each of the series are positive, the sequence of partial sums for each series we call it monotone increasing. Now, if we think about this, what we're really trying to demonstrate here is this right here. Does it fit in the middle? Because if I go back up into my definition, that has to be in the middle of 1 over n squared and 0. So this is what we have. We got to make sure that these are in the middle. And when you go ahead and you think about this, all right, you are basically keeping the numerators the same. Your denominator is going to be a little bit different. So let me kind of demonstrate this. So if I have, let's say, n 1 over n squared plus 1 and 1 over n squared, and I just started picking, let's say, some values of n, and I'm just randomly picking these. Actually, you know what? We'll pick nice ones. Whatever. That's fine. All right. Here's what we have. When n equals 1, we have 1 over 1 squared, which is 1, plus 1 is 2. And this is 1 over 1. And clearly, 1/2 is less than 1. Now, for n equals 5, we're going to have, in the denominator, 25 plus 1, which is 26. So it's 1 over 26. And you're comparing that with 1 over 25, and yes, that is smaller. Then you have 1 over 101. And yes, 1 over 101 is definitely smaller than 1 over 100. And what we can say is, since our series of 1 over n squared converges, and each term in the series so I'm just going to write out the series. Is less than what we're comparing it to, by the comparison test the series of 1 over n squared plus 1 must converge. And that's it. That is pretty much all you have to say. All right? You compare it with something that you know converges. And if you know it converges and all of the terms in this series that you are given is less than the one you're comparing it to, and as long as it's positive increasing, you can say by the comparison test, the series from 1 to infinity of 1 over n squared plus 1 must converge. Now, let's look at the other side of this. So let's go back up to the other property. Suppose there exists an integer n such that the sequence that you are given happens to be greater than one that or greater than the other that you're comparing it to. If b sub n diverges, so does the other sequence. All right? So let's look at a really nice example. All right, let's do this one. Does the series 1 over n minus 1/2 converge or diverge? Now, this looks like a series that we know. In fact, this looks like one over n. And we know this is a monotonic and it diverges. So the only thing we have to show here, if we think this diverges because it looks like something that we're familiar with, we're just going to make sure that the terms are going to be bigger than the one that we're comparing it to. So the terms a sub n have to be bigger than b sub n. So let's go ahead, let's do that. So the sequence of partial sums for each series is monotone increasing and our series a sub n is going to be greater than b sub n, which is greater than 0 for every single integer n. So, like I said, let me show you what this looks like first. We're going to do the same exact thing. N 1 over n minus 1/2 and 1 over n. Once again, I'll pick the same numbers that I did last time. 1, 5, and 10. So, excuse me, we will start off with n equals 1/2. I'm sorry, n equals 1. You get 1 over 1/2, which turns out to be 2. And then here we have 1. So we know 2 is greater than 1. Now, let's do 5. So we have 5 minus 1/2, which turns out to be 1 over. Sorry, my cat's jumping all over me. 9 over 2, which turns out to be 2 over 9. And 2 over 9 is greater than 1/5. Finally, we got 10. So we have 10 minus 1/2, which is 19 over 2. So it's going to be 1 over 19 over 2, or 2 over 19. Over here, in the third column, we get 1/10. And 2 over 19 is greater than 1/10. So we're showing that it increases, and it's always going to increase for however many terms you go. Thus, the series of 1 over n is a known divergent series, and the series that we have is greater than our known divergent and I'm just going to write it like that, just so this right here just tells me it's all the terms are greater than b sub n. Our series must diverge also. And that's it. Now, I do have a little picture here that we can see. And here's what all the partial sums look like. So if you look at our first graph, here is all the partial sums for 1 over n squared. Here are the partial sums for 1 over n squared plus 1. And you can see that it's less than 1 over n squared for every single term. So because this diverges, I'm sorry, I said the wrong word. Because this converges, that automatically implies that this is going to converge as well, because it's even smaller. On the opposite side, though, since we know this diverges, that means that our sum, or our series 1 over n minus 1/2, has to diverge also, because every single term is greater than all these terms right here. Okay? So that's what a comparison test does. You don't have to make this any more complicated than what it is. Like, for example, if I wanted to say, or if I want to ask this question, does, from n equals 1 to infinity, does the series 1 over n cubed plus 3n plus 1 converge or diverge? All right. Well, This is very simple when you think about it. All right. So basically what we have here is this. Oops. When n goes to infinity, these two terms right here mean absolutely nothing. Because your n to the third power is going to dominate what happens. It's the leading term, it's the highest degree. Now, what I do know is this. Even though I have n to the third and it's dominating, I'm still adding a very small amount. Okay? And that will always be less than the p series of 1 over n cubed. Like, I know that. So because this is always increasing, it's always positive, and a sub n, which is this, is less than b sub n, which is this, our sequence, or I'm sorry, our series is convergent. That's it. That's all you got to do. That's all you got to do. Okay? So, in the next video, we're going to go over the limit comparison test.